So welcome. So in this video we will discuss about the design of continuous slab. So where we go for a design of continuous slab. So multi-story building. So in this multi-story building it comprises T-beam, then slab, again like a T-beam. It will like that continuous slab. So instead of design for simply we split it as a one-way slab, two-way slab like that, we will take it as a continuous slab. Then we will design for that. It will be easy to calculate the bending moment, shear force, and as well as the load, everything. So T-beam and slab. So it is spaced equally for the one beam to another beam and one slab to another slab. So for that cases we go for a design of continuous slab. Otherwise it is very simplified approach. It is simplified approach to design the continuous slab. So in the IS 456 they recommended some of the moment and shear force coefficients. So based upon the coefficient it will be, the value will be very actual bending moment and the shear force. So for the, as we are designed for the continuous beam, we are going to design for the continuous slab also based upon the moment coefficient and as well as the shear force coefficient. So where we can refer the coefficient means in IS 456 page number 35, 22.5 that. So IS 456 page number 35, moment and shear coefficient for continuous beam. They provided all the details for the shear coefficient, moment coefficient calculation, and as well as they mentioned in table number 12 and 13 to the next page, page number 36. They mentioned here table number 12 bending moment coefficient and as well as the shear for coefficient. So we have to refer for the dead load and imposed load and imposed load. So after getting this value, that is coefficient value, we have to multiply for they mentioned in the table itself. For obtaining the bending moment, the coefficient shall be multiplied by the total design and the effective span for the calculation of bending moment. Whereas shear force, for obtaining the shear force, the coefficient shall be multiplied by the total design load. So we have to refer page number 36, table number 12 and 13 for coefficient, and finally we will calculate the bending moment and shear force for the continuous slab. So this is the design procedure to calculate, and we have to design for the continuous slab. So first of all, how the question will be provided, how the data will be provided, we will let's see. Design of one-way slab. As we are designed already one-way slab and two-way slab, so based upon the question itself, we should not go for this is one-way slab. So further we will read the questions. In the office floors, which is continuous? That is the word very important. So design of one-way slab for an office floor which is continuous over the T-beam spaced at 3.5 meter. So we will assume some of the loads. Live load is 4 kN per meter square. Concrete is M20 grade of concrete is used. Then FE HY bars we will provide for the continuous slab. So step number 2, we calculate the depth of slab. So assuming span by depth, since it is a one-way slab provided in the question itself, in the page number 37 itself, we already discussed for the continuous slab 26 meter, we will assume, we will take it from the IS 456. So span by 26. So whenever we consider for the, here length is 3.5 meter, so span by 26, 3500 divided by 26, which will get 135 mm. So we will assume 140 mm. So overall depth 140 plus we assume 10 mm dia bar, so 10 by 2 plus 20 cover. So overall depth is 165 mm. Okay, is it clear? So next we will go for a load calculation. So in this the continuous slab, we will calculate the dead load separately and as well as the live load separately, because of we go for a take the moment coefficient as well as the shear coefficient, so it will be very easy to identify separately. So self height of slab, as we are overall depth is 165 mm into 1 meter and 25 kilonewton per meter cube, so 4.125 kilonewton per meter self height. Then finished load, we will assume ourselves 0.875 kilonewton per meter, which will be total load. Combined is total load, so total load we consider as a G, taken as a G. So 5 kilonewton per meter dead load. Then live load, we will assume 4 kilonewton per meter, we will take it as a Q. So from the continuous slab calculation up to loads, self height of the slab 4.125, finished load 0.815, dead load we submit up 5 kilonewton per meter, so live load 4 kilonewton per meter. So step number 4, bending moment and shear force. So as we have discussed, we need to refer table number 12 and 13 of IS 456. So first of all, we need to calculate the maximum negative bending moment at the support, then maximum positive moment at the center. So these are the two categories which is we have to refer from the table number 12 and 13. So in that case, they provided the provided the support condition, span and the support moment. They provided here dead load and imposed load. So here -1/10, -1/9 they provided, and as well as the for the center of the span they provided as the 1/12 and 1/10 as well. So this is 1.5 for the ultimate moment. So 1.5 times of G is live load, Q is dead load. So Q is dead load, G is dead load, Q is live load. So 5 into 3.5, our L is 3.5 meter span. So 4 into 3.5, WL square by 8, that formula only. But here, as we are coefficient is there is a provided the factors. That's why we need to replace it. So Q L square by 9. So substitute all the value, we will get the negative bending moment for the support 17.35 kilonewton meter. Maximum positive bending moment at the center of the span. So since we are referring from the table number 12 and 13, the maximum bending moment 1.5 times of GL square by 12 instead of QL square by 10. So 1.5 times of 5 into 3.5 square by 12 plus 4 into 3.5 square by 10. So we will get the 15 kilonewton per meter. Almost only 1 to 2 kilonewton meter only differs for the support and the mid. So next we will calculate the maximum shear force at the support. So 1.5 times of from the table we will got the 0.6. So 0.6 times of dead load plus live load into length. So 1 times 0.6 plus 5 plus 4 into 3.5, which will get the 28.35 kilonewton for the maximum shear force. So next we will have to check whether we founding our effective depth is withstand that. So mu limit formula 0.138 FCK BD square. So substitute all those values, we will get the 59.1. So our mu value is here maximum is 17.35, so which is less than 59. So since it is a mu less than mu limit, based upon our conditions, it is under reinforced. So next we will provide the reinforcement for end support and as well as the mid span. So for the end, substitute that moment formula, we will get the AST of 360 mm square. So we need to provide at least 10 mm dia bar. So 10 mm dia bar at 150 mm center to center support. So here negative bending moment and as well the positive bending moment more or less equal. So that's why we straight away we provide the reinforcement, same reinforcement what we provided for the end, which is same reinforcement provided for the mid also. So provide same reinforcement of end support for positive bending moment at mid span. So here also we provide 10 mm dia bar at 150 mm center to center support. So step number 7, distribution reinforcement. So here the formula is minimum reinforcement for the slab is 0.12% of B into D. So that is cross section. So 0.12 by 100 into 1000 into 165, we will get the 199 mm square. So we provide 10 mm dia bar at 300 mm spacing, that is the maximum spacing, we know that. So AST for the that 10 mm dia bar AST is 262 mm square. We enough 198 mm square is enough, but we provided the 262 mm square for the 10 mm dia bar. So next step number 8, check for shear stress, that is tau V by Vu by Bd, and we need to compare with the tau C value, nominal shear stress and the design shear stress. So here nominal shear stress is Vu by Bd. Vu is nothing but the maximum shear stress, 28.35 into 10 power of 3, 1000 into 140, we will get the 0.2 Newton per mm square. So we need to compare with tau C. So tau C PT value 100 AST by PD. So here AST is what we are provided. We have to provide here 262 mm square. So 0.187 percentage of tensile reinforcement. So now read out IS 456 table number 19. We will get the, this is factor, the depth we provided for 165 mm, that factor is 1.27 into 0.3, we will get the 0.38 Newton per mm square. So as we compare with tau V, it is very less. Tau V is greater than the tau C value. So hence slab is safe. Slab is safe against shear stress. So next we will need to check deflection control. So maximum deflection, actual deflection. So maximum deflection is formula L by D basic into KT into KC into KF. Here we need to consider two places, one is end and another one is interior. So for the end we will get the 20, for the interior we will get the 26. So L by D max we got the 34.5, then L by D actual we will get the 25. So your actual is 25, maximum is 34.5. So it is safe against deflection. So again we will conclude the design of continuous slab, which is reinforcement details. So what we are designed so far, we need to provide as a diagram. So here is the reinforcement detail diagram. So overall depth is 165 mm. This is support. Center support is 3.5 meter. So reinforcement, what we have provided here, both the section we provided 10 mm dia bar only. Only spacing is differ. So this reinforcement 10 mm dia bar, 300 mm center to center spacing. These two 10 mm dia bar, 150 mm center to center spacing. So this is the reinforcement detailing diagram for continuous slab. Hope you all understand the concept. So thank you all.